Okay. So what I'd like to do is to carry on from the talk that we did last Thursday. So what I'd like to do is to go through something called extensible classes. This is something that we implemented in the compiler technology, and if you haven't really seen this before, it might strike you as a bit strange, the way that we've sort of structured the classes. Not all classes, just some of them. And what I'd like to do is sort of talk about the reasons why we do that and what the motivations are and how they all fit together and how they work and how you can create them. Because when we're talking about creating new stuff for ARM, for A64, if we're talking about a new backend, we're going to have to create extensible classes because some of the fundamental data structures are extensible. You don't necessarily need to understand them in great detail, but I think this is going to help you. So, okay, so I'm just going to give a little bit of history behind this. So when we started looking at open sourcing a lot of this compiler technology back in 2013, 5 years ago, you know, we had the technology was used across a fairly broad spectrum of compiler technologies, so Java, C++, COBOL. That's just sort of a handful. There was a variety of different consumers of this technology, and when we started thinking about you know, what we were going to do with this technology and how it could grow, you know, we wanted to think about how this technology could be used in the cloud. So that led us to distilling the core components of this compiler technology into an open source toolkit of reusable, customizable, language-agnostic compiler components. So this was our effort on pulling apart the compiler technology. It was actually part of a much bigger effort with the Java technology to make that more general and reusable as well. And at the time, we decided to call this the OMR project, and eventually this did all get open sourced in 2016, and it's the thing that we're working on right now. So that's sort of where and why it came about. So how are we going to do that? So how are we going to take that technology in the compiler and open source it? So, well, what we did was we started with the very large blob of code that was Testarossa, and at that time it was about 1.5 million lines of code. And what we did was we identified basically the core pieces of that would be interesting enough to be able to build parts for other compilers and other language runtimes. So, for example, things like symbols and instructions and you know, registers, that kind of thing. All these different kinds of classes that you'd find in that technology, they're definitely applicable in other compilers as well. And then once we kind of gone through that, we sort of figured out what parts of this technology could somebody actually extend. Because and what is where will they get their hands on the different parts to extend? So things like classes, for example, can you extend a class? We have a lot of data that's sort of represented as enumeration. So can enums be extended? Or if you look at things like the IL opcodes and instructions, things like that, they're all stored in these static tables. So is it possible to extend those as well? So we needed to figure out what all these different parts are and then come up with a solution within OMR such that these things can actually be extended. So what do we want extensibility to achieve? So we have a number of goals here. So first off, and perhaps one of the most important ones, is really to isolate features to specific projects. So if you start off with a base layer of compiler technology that provides a very common, very low-level kind of support for a variety of different features, different projects like Ruby or Java or different architectures like ARM or SH4 or something like that, they can come along and specialize those like those base features the way that they want them to, and they can actually extend them as well. But when these projects, come along, you don't want the requirements of a particular architecture or the requirements of a particular project like Ruby or Lua to actually start injecting some of those requirements into the base layer. You want to keep that as nice as possible, nice and clean as possible, and as language agnostic as possible, because that is really one of the design goals behind Eclipse OMR. So we want to be able to isolate features to different from different projects. We want to minimize the impact to compilation metrics, things like startup, compile time, and footprint. So if we're starting to create extensible, extensible compiler technology, there are a number of ways that you can do this, and we don't want to introduce an extensibility mechanism that's going to impact one of those metrics in a very negative way. Up until this point, as we were developing this technology for the past, 15 or I guess 18 years, whatever it happened to be, we had spent a lot of time making sure that all those metrics were very carefully adhered to, and we performed well in all those cases. So we don't want to introduce something that's going to blow all that out of the water. We also want to minimize any sort of future merge and integration costs of projects that may be consuming this. So it wouldn't be a great strategy if we came up with an extensibility mechanism that wasn't easy to consume by another project. If every time you wanted to pull in a new Eclipse OMR, for example, we put a bunch of new features there, somebody wants to consume it, it wouldn't be a great story if they had to do a lot of work to basically integrate that into their project. So it had to be sort of a nice, clean, simple way of integrating into those downstream projects as new things were added to Eclipse OMR. We also wanted to be able to allow future extensibility, beyond what we can currently think of, and or even for projects that don't even exist yet. So we want to make sure that whatever solution we came up with was flexible enough to do that. And the last thing here is that the solution must be compatible with the existing code base, and it's supported by multiple build compilers. So we had as we were going through this exercise, we decided that we were going to stay with C++ as the implementation language, and any solution we came up with really had to work within the constraints of C++ and the level of C++ that was available on build compilers that were available on all the platforms that we support. So this includes things like all the processor architectures, but also things like ZOS and AIX and Windows, all those, we had to sort of take the lowest common denominator about all those and make sure the solution works there. So those are the goals that we wanted to keep in mind as we were designing something. Oops, what did I do? Was there a question or? Okay. If you have a question, by all means, just jump in anytime and interrupt me. So I don't mind that at all. Okay, so just to give you a bit of a historical context of our starting point. So when we started thinking about solutions to this, they were very heavily influenced by the state of the world at that time, which is 2013. And like I said before, we were a project that had, I think, at least 6 or 7 different projects that were sort of extending from it. Java, there were static languages, there were binary emulators, there were binary translators, lots of different stuff, all totaling about 1.5 million lines of code. And perhaps one of the key things that really influenced a lot of our early design was the fact that a lot of this technology, a lot of these components were very strongly connected, and it would have been, ideally they shouldn't have been, but I think the way that they all had kind of evolved over time, they sort of started to develop dependencies on each other. So we had this situation where all these components were fairly strongly connected, and we had to do a lot of work to basically break a lot of those dependencies. The other thing about going forward here was that our expectation was that any work that we did here was all the projects that were going to be consuming this kind of technology well, they were going to be able to extend it as they wanted. So, so Java, for example, we knew that was going to be open source. We open sourced that last year. There was some technology that we knew were never going to be open sourced, or they're not going to be open source in the short term for sure. So things like COBOL, for example. And yet we still wanted to be able to share all the stuff that we were doing across all these projects. So we needed a solution that was going to work with, you know, closed source stuff and open source stuff, and have it all fit together. So that was sort of our mindset and our starting point here. So what did we finally come up with? So this wasn't the first solution. I think this is about the fourth solution that we had eventually came up with. It was a very iterative process. We went through a lot of sort of trial and error and what worked and what didn't work, and I was mentioning C++ before, and I'll say that it was really it really influenced a lot of our thinking here, like the limitations of C++ and the capabilities of C++ really influenced a lot of this. So what we came up with was a composition model for extension, and the way that it really works is a lot of the way that the classes and other things are put together are really driven by the order of the files that are found on the include path. Because when files are starting to get included, they need to get included in the right order. And it's certainly possible that you may have multiple implementations of something in your overall project, but depending upon what the iPath is, it will only find one implementation that you care about when you're doing your build. And we'll get into all that a little bit later. And the mechanism, it uses you can extend a couple of different things. So you can extend class definitions, or you can actually provide inner parts of data structures to extend. So classes are a little bit easier to extend just by the way that you can actually just continue to subclass them. But things like enumerations are a little bit more difficult to do. But what we've done is we've sort of taken out the inner parts of the actual data parts of those data structures and allow you to compose those across multiple projects. And we'll see an example of that a little bit later. Just some terminology. A compiler product is built using a hierarchy of projects that target a particular architecture. So when we're talking about projects here, we're talking about, like OMR, for example, is a project. OpenJ9 is a project. Like Ruby or Lua would be a project. And a product is really something that is built from a hierarchy of those projects. And any of these projects can actually provide processor specialization as well, right? So you can actually have x86 specialization or ARM specialization of pretty much any class that's in this hierarchy. The way that the extension mechanism works is that projects do extend other projects, and within a single project, like I just said, you can do extension and specialization by architecture. The one kind of rule we have through all this is that OMR must always be the primordial project. It must always be the base of the hierarchy. You can't, for example, put something before it and have OMR derived from it. A lot of things are going to sort of fall apart if that happens. The other requirement that this imposes, and I guess we'll see that in a little bit, is that it really does require a symmetric directory structure between projects. And what that means is that, like if you're creating CodeGen classes, they all have to live in the CodeGen directory on every single project. And the reason this is necessary is because of the way that this whole thing is really dependent on the iPath, right? You need to be able to find things in a very symmetric way using the iPath. So a little bit more on that. So the include path enforces a search order over the products to make sure that only the most specialized extensions are discovered first. So like I said on the previous slide, you can have multiple implementations of something in your project, but depending upon how you want to build it at this moment, the iPath will find the right extension that you are interested in. And each product is actually responsible for setting the iPath that makes sense for that particular build. So the assumption behind a lot of this technology is that you're only going to be building for one particular product and one particular architecture at once, right? So you're going to be building PowerPC and Ruby, right? That's the combination that you're going to be building. And depending on that combination, you would choose an iPath that selects the PowerPC and it selects the Ruby projects in the right order. You don't care about stuff that's been implemented for Lua. You don't care about stuff that's implemented for the Z processor or ARM. It doesn't matter. It's the iPath that makes sense for that particular project. And the way that the whole thing kind of fits together is by making sure that when you use these include directives, you have to use a path. You can't just have the file by itself. You actually have to have a stem path, and you can't or you shouldn't be including a project. Like in this particular example here in the third bullet, it talks about TRJ9. That's really not something that's recommended, except in very select circumstances when that truly is required to specify a project. If you want, for example, to include the code generator, you should just include codegenerator.hpp, and depending on what the iPath is for this particular product, it'll find the right code generator that should be included. You shouldn't have to tell it, find me the TRJ9 one. The other little challenge with some of this, with the way that some of these files are put together, is that if you're really dependent on using an IDE for doing your development and for navigating your code, you may have to provide a specialized iPath for the very specific project that you're working on. Like if I'm editing code for x86, for x86 and Java, I need to set up the iPath correctly in my IDE to be able to find all the parts that I want. Otherwise, if I do a search for a code generator, for example, I might be finding stuff in the Z code gen that's not interesting to me at all. So just something to be aware of if you're using IDEs to edit your code. So what does a typical iPath look like? And this is an example from OpenJ9. And things actually look a little bit different now. We don't have a tr.source directory anymore. But basically the interesting things here is that the ordering of this is very important. And you basically define your iPath on the most specialized project all the way up to the least specialized, where the least specialized is always OMR. So in this particular example, you can see that we're starting in the J9 project. The X directory there, I don't know, can you guys see my arrow here? The X directory here refers to the fact that this is an x86 architecture specific directory, and AMD64 is a further specialization of that. We call that a sub-architecture. So if something isn't found there, the next directory it'll search is the next least specialized, which is just TRJ9X, so just x86. And if it can't find anything there, it'll look in, it'll look in just somewhere in the J9 project if it can find stuff. So it'll basically walk its way out of this project. It'll then do the same kind of thing in the OMR project as well. And eventually, it should find something. And in the worst case, you would find something in the most general OMR layer here as well if you haven't provided any specialization. The way that a lot of this is written as well is to use C++ namespaces, and it's really to help us control the scope of the code, and to keep things isolated to certain to certain projects and certain architectures. If you look at the top level namespace is OMR, and that's reserved for OMR technology. And then when you look within a particular project, so first of all, after that, you can basically use any namespace you want for the technology you want. So for example, OpenJ9 uses J9 as its namespace. If you've ever looked at Ruby code, it uses, surprise, Ruby. But pretty much any other name is available. Now, within a particular project, we also use nested namespaces to describe architecture and sub-architecture extensions. So I listed a few of them there. Actually, that's probably all of them, to be honest with you. Power, x86, the even further nested for x86, AMD 64, and so forth. There is one special global namespace that we use in this technology, and that's TR::. And it's used for something that we call concrete classes. And what these are, and we'll talk about that in just a second, but when you are actually composing an extensible class, you're actually composing these from what we call extension classes. And then at the very end, once you've gotten to a point where you have specialized it all as much as you want, what you do is you actually have to produce what we call a concrete class that somebody can actually come along and instantiate. So that's sort of a public interface to your extensible class is something that's in the TR namespace. And TR::, is something that can be used in any project at any time to get the complete extensible class that you've just produced. Okay, so I just said extensible classes, so I guess I should maybe define what we're starting to talk about here. So an extensible class is really a class that can be composed of specializations from different projects, and it can be multiple projects at the same time, or it can have multiple architecture specializations as well. Now, it should always be a particular extensible class should only have like one architecture. Like you're not going to be extending something for x86, and a little bit later on in this cycle you're extending it for power. It should be one sort of uniform extension. The composition is achieved through single inheritance, and it's extending these things like I just mentioned called extension classes that each project must provide. And if you're familiar with CRTP, the curiously recurring template pattern, which is a way of doing static polymorphism in C++, you'll notice that it's a very similar technique to that. We did investigate using CRTP as a way of doing this, and it turned out to actually not work as well as we had hoped, and the reason was because of its use of C++ templates. So the way that CRTP works is that you sort of pass up the most derived class as a template parameter to all the other classes in the hierarchy. And the problem with using templates is that it requires, in many cases, if you're going to start using templates, it requires the definition and the declaration and the template implementations, all that, to all be visible at once. And when I talked earlier about the fact that we were a very strongly connected component, that was a problem early on because it required us to basically pull in the entire world just to be able to extend a class. And the reason you had to pull in all this stuff is because of the templates. And so early on, this wasn't a great solution for us. We couldn't really get this to work. So we decided to get rid of the templates and do everything sort of manually, the static polymorphism manually. The other thing I should mention as well is that just because we have extensible classes doesn't mean you have to use them. It really depends on what it is that you're trying to achieve with your particular class hierarchy. Perhaps it's something that you don't expect will ever be extended, or perhaps you don't want it to be extended at all. So it really depends on what you need. So why are we not using virtual functions? Why are we going with static polymorphism? So performance is really one of the key reasons of this. When we had first started this work in 2013, there certainly was some immaturity with some of the compilers in doing devirtualization. There were serious performance problems on some platforms as well when you had a lot of virtual functions. And keeping an eye on like our compile time performance and our startup performance, which has always been very critical for this technology, the lack of inlining opportunities could add up over time with the fact that we couldn't inline code. You basically always had to call a virtual function. The other thing is that the points of extension within this hierarchy are now virtual functions. Like that is how you extend a class, is with a virtual function. And there was some concern around the performance consequences in downstream projects. And one of the examples that we used a lot when we were thinking about this was, if you take a very common function that there is right now, like is 64-bit target, it's a question you ask the compilation to see if I'm compiling for a 64-bit target or not. If suddenly that query is used everywhere, and right now it's not virtual. If you wanted to make that an extension point, and in the future, and we came along, and our only means of doing that was to basically make it a virtual function, that's going to potentially add a fair bit of overhead that's going to impact all downstream projects because it's used so often. So if somebody suddenly adds a virtual keyword to something, then that could potentially disrupt a lot of things. So we need to be careful about that. And then perhaps the other reason that motivated a static polymorphism approach is that when you look at what we're actually trying to achieve here, when we're actually putting a compiler together for a particular architecture or project, there's not really that many structures that are dynamically polymorphic. We don't really need to use the dynamic polymorphism mechanism, right? So you can pretty much figure out at compile time what your hierarchy is going to be and what classes are going to be extended. So you can potentially unlock a lot of performance that way. So a lot of these things sort of pointed toward a static polymorphism approach. So that's what we decided to go with. Okay, so I'm going to take you through a few examples now. The first example that I'm going to show you with extensible classes is really a very abstract, no-code kind of idea of how these classes are put together. So let's say that, let's start on the base layer, and we want to create some kind of an extension, some kind of a class. It's going to live in OMR, and we just create some code for it. What you can do is come along and provide some power specializations to that class. You can also provide some x86 specializations to that class. You can come along and do even further refinement of the x86 specializations for 386, or you can do nothing at all. You can basically just not want to extend it at all. So once you've got these extension classes, what you then do is you have to create a concrete class that will represent the that kind of an extension. And the way that concrete class works is that it sort of extends. It can extend each of these different architecture extensions that we have created. So, as it says here, an extension class is a class that is used in the composition of an extensible class. It has to live in the namespace of the project that provides it. So in this case, each of these extensions have to live in the OMR namespace. If we were in the J9 project, for example, they would all have to live in the J9 namespace. The way that the specialization works is through class inheritance and method overrides. So not virtual, but just pure method overrides. And the thing about the extension classes is that they should never actually be instantiated themselves. The only place where they should be instantiated is through subclassing them. You should never have to come along and create an OMR. Like if this class is called my extension class, you should never actually have to create an OMR my extension class. You should only ever be instantiating the concrete class, which is what this is trying to say. So what the concrete class is, it's really an external interface to the extensible class. So it is the thing that is actually instantiated when you want to create this class. And it lives in the TR namespace. And what it really does is it just inherits from the most specialized extension class in that project. So in this particular case, depending on what and how you're building, it could be extending from power, it could be extending from x86 or 386, or it could be extending nothing. It could just be going straight to the, I don't mean nothing, no architectural specialization. It's coming directly from the extension class itself. So the question then is, how do we figure out what class needs to be extended? Like, how does the concrete class figure out which one is actually extending? Oh, okay. Before I get to that, I guess there's just a further refinement here. When you actually end up building these things, you end up producing an effective class hierarchy. So if I'm building this project on Power for a Power architecture, this is what the class hierarchy is going to look like. You know, given the way that the iPads work and all that kind of thing, this is what the class hierarchy is going to look like. So you're going to have a base layer, the Power extension, and then the concrete class is going to extend from that. You're not going to see any of the other stuff for any of the architectures. It's purely just going to be just Power. Same thing for x86. The 386 extension looks like this. So the concrete class would extend 386, but 386 also extends x86, which extends the OMR extension class. And if you had no specialization at all, the concrete class would extend the extension class directly. Okay, so that's the question I asked before. So how does the concrete class know what class to actually extend? Well, we define something called a connector. And each extension class has to basically provide a type def of itself to a connector in that project. And then the iPads and other sort of pound-defined magic come into play to ensure that only one connector per hierarchy will actually be discovered in any particular product build. And when you have, so concrete classes, or if you have another project, for example, like J9, the way that it actually will extend something in this base extension class, what it actually does is it actually extends the connector. It doesn't actually extend any particular extension class. It's only extending the connector. We'll see that in just a sec. I'm not saying that very clearly, I don't think, but I'll show you an example in just a sec. Right. So what happens here is that each of these architecture extensions, or in the case of the OMR extension class, it needs to provide a connector as well. So each of these guys is supposed to be providing a connector. It's got a common name that, depending upon what the iPath is only going to be seen. Only one of those is going to be found. And if you want to extend this, if you want to have another project that extends this, like OpenJ9, for example, all OpenJ9 will do, it'll provide its own extension class, but then that thing just simply extends the connector. It doesn't care that it's a Power implementation or an x86 specialization or whatever. All it knows is that it needs to extend the connector. However, you can come along and extend OpenJ9 with Power extensions or Z or whatever. And then, of course, you also have to provide a connector for OpenJ9. And then you have to build a concrete class that extends that OpenJ9 connector. And that concrete class will live in the TR namespace. Okay, so I thought that what I could do next is to actually show some code. I'm hoping that that'll answer some of the questions you might be having. I have to say about this kind of technology, it does take a little bit of getting used to, but I think that if you did spend a bit of time just looking at the code and the way that the classes are structured and the way that the build files are actually structured, it's fairly straightforward to figure out. But anyway, I think an example here with showing you real code might help as well. So this is an example of the instruction hierarchy. So starting at the very base layer in the OMR project, we're looking at the header file that basically describes the API for the instruction class. It lives in the CodeGen directory, and this particular file name is omrinstruction.hpp. So that's particularly important because all extension classes for a given class, all the extension classes in the same project should have the same name. So anything that's going to be extending OMR instruction.hpp should have the same name, OMR instruction.hpp. And they're never going to live in the same directory. They're going to live in different directories. Like if we had an x86 specialization or a Z specialization, as we'll see in a couple of slides, it'll live in a different directory altogether. Yeah, so all extensions within this project must have the same base file name for the connector work to operate properly. The first part of a lot of these these extension classes is to really define the connector. So basically, if the connector hasn't been defined before, if we haven't seen one before, we need to actually create a type def to the connector. And what it's really doing is that for the instruction class in the OMR project, what it's really doing is saying, okay, there's only going to be one instruction connector name. Anything that wants to extend the OMR instruction will always just look for the instruction connector. Like, it's going to look for that one name. It's not going to look for it. I don't care that it's in x86. I don't care if it's in Power. It doesn't matter. I'm just going to look for that one name. So the connector is an instruction type def name in the OMR namespace. Okay. When you define the class itself, the API for the class, as you can see, it lives in the OMR namespace. And we've also defined this sort of special attribute that it's a macro, but it actually will map to an attribute for most build compilers that really describes the fact that this is an extensible class. And the only reason that this exists is that we have some tooling as part of our build that will check that these class hierarchies are formed properly, and that certain rules about forming these classes are being followed. It's actually fairly useful to detect certain kinds of errors. We'll see those in a little bit, but it's useful for finding those kinds of errors. But you should use it. Things will still work if you don't use this, but it's very highly recommended that you do. Okay, so this is a source file, and you can pretty much call the source files whatever you want. When it comes time to actually consuming extensible classes, you basically pick and choose the file names that you want and put them in the makefile list, right? So you can call them whatever you want as long as they live in separate directories. So, but it is useful to keep the names consistent, I find. So. Here, you don't actually include, so this thing wants to include the OMR instruction class that we just created. It doesn't actually include OMR instruction.hpp. It's actually using the concrete class header file because this is a CPP file. And we're going to see an example of the concrete header file in just a bit. So we're still in the OMR project. And let's say now that we actually wanted to provide an architecture specialization. So in this case, we wanted to provide a Z architecture specialization. So that's fine. So the first thing that we need to do, just like the other file, is to actually create a connector. And notice how the name of the connector is still the same. It's in the OMR namespace. It's called instruction connector. So the name is still exactly the same as it was in the base OMR instruction.hpp. But given the way that well, actually, I should go through this in the right order here. So the first thing to note is that fact that the name of the file is the same as the file in the base class. So it's still OMR instruction.hpp. Right, so I just said that about the OMR, that's the same name for the instruction connector. So given the way that if your iPath is set up correctly, like we saw before, it should be from the most specialized to the least specialized. If it's set up correctly, if I'm building on Z, you should find the Z instruction class specialization before the just the OMR base class. So you should find this OMR instruction at HPP before the one that lives in just CoGen OMR instruction at HPP. And it's easy to check to see if your IPath is incorrect, because if we had already seen that the instruction connector was defined, that means that we had already processed the base class or something else. And if that's the case, something is very out of whack here, and we should be able to die at compile time here. And we do. So that's what this particular error means, if you happen to see that. So because this is a Z architecture extension, and it's going to be extending the base OMR instruction, it needs to basically reach back and include that base class. So here's an example of where you should use a project-specific path. So in this particular case, the way that this stem path is written here is it's going to find the parent of this particular class. And then when you are extending it, we also see that this is now in the OMR namespace. It's got the Z nested namespace as well. You still say that it's an extensible instruction. And what it's deriving from is OMR instruction. So this is its immediate parent. So the Z architecture instruction, the Z instruction specialization is going to be extending the OMR instruction. It's not extending the connector, because we're within a project, so it's extending the instruction itself. Okay. So this now drops into another project. So if we now wanted to say, okay, J9 wants to extend the OMR instruction with its own, with whatever it wants, we're now in a different project. We're now in TRJ9. And what it's doing is it needs to basically do the same kind of definition as you saw in the base class. So now we're in the J9 namespace, and you basically have to now create a new instruction connector for the J9 project. So he's now creating a J9 instruction connector that at this point is pointing to just the J9 instruction. And the next thing to note here is that this particular project, this particular extension is going to be including, it's extending the OMR one, so it needs to include the OMR instruction at HPP. And this is now why it's important for all those files to have the same name, because I'm in a different project here. I'm in J9. I don't know, I don't care, you know, what, well, I don't necessarily care which OMR instruction I'm actually extended. All I know is that here is some J9 specialization for whatever's been provided in OMR. So this OMR instruction at HPP could be coming from Z, it could be coming from the base, it could be coming from you know, maybe ARM, something like that. It doesn't matter. All I do is specify CoGen OMR instruction at HPP, and the IPath will figure out, depending on what my target is, it's going to figure out the right file to include here. Right, and so here where it's defining in the J9 namespace, its instruction class, again, you have to say OMR extensible. Now the thing that it's actually extending is OMR instruction connector, because you don't really know, when you're writing the source code here, you don't really know what it is that you're extending, you know, if it's Z or X or whatever. So all you do is now you use that connector name, and that's what makes it all sort of fit together. So this now is an example of a concrete file, or a concrete class definition. So the name of the file is now instruction.hpp, and you'll remember from the CPP file that this is the name that we actually used when we were including in the CPP file. So so the way that this actually works is that because this particular implementation lives in TRJ9, he has to include the J9 instruction.hpp. There would also be a similar one in the OMR cogen instruction.hpp, but it would include cogen OMR instruction.hpp. So whichever level of the hierarchy you have your instruction.hpp, you have to include that you have to include that project's instruction.hpp. And of course, the IPath will figure this out for you. This is where we put this in the TR namespace. And what it's really going to be defining here is a TR. In the TR namespace, it's creating an instruction. So anytime you want to create one of these things and create an instruction, you're actually creating a TR : instruction. That's what it's going to find. Okay. So I guess I can pause there for a sec to see if there's any questions. I know it might take a little bit to absorb a lot of this, but I can pause if there's anything that anybody wants to ask. Okay. Okay. If not, we'll go on to the next kind of feature of this. So that's how the hierarchies are kind of put together. One thing that is necessary, and this is particularly important for anything that uses static polymorphism, is that in order to make sure, so the way that this hierarchy kind of looks, it's sort of upside down from a dynamic polymorphic hierarchy, because in the dynamic polymorphic hierarchy, you kind of have a pointer to the base of the hierarchy. In this particular case, you actually have a pointer sort of to the most specialized class. So in order to make sure that you're going to be, if you want to make sure that you're calling the correct function somewhere in this hierarchy, you want to make sure that you're calling the most specialized, and you don't have the virtual keyword anymore to help you. It doesn't sort of resolve this at runtime. So you have to make sure that you downcast anytime you want to use something from the this pointer, you basically have to make sure that you downcast that to the most derived class and let the compiler figure out what the implementation is to call. So this is I guess a common technique in static polymorphism. So what this is saying here is that calling the most specialized member function in an extensible hierarchy requires a static cast of the receiver to the concrete class. So yeah, so basically just using the static cast keyword in C++, you cast it to the most derived TR : class. Without a downcast, the implicit receiver is this in the dispatching class. So if you don't do this, then the problem that'll happen is that if you just call a function that's been extended, let's say foo, in some class in that hierarchy, it's going to find the foo in that particular hierarchy. It's not going to find any sort of specializations that you may have done on that. So in some cases, you're going to get the wrong function being called. And we have had some fairly subtle bugs found because of this. In fact, I think James even found one recently with ARM because the wrong one was being called. Maybe not too recent, maybe a little while ago. But each extension class has to. So the way that we've make this a little bit easier to get around is that each extension class should provide a self method that performs the explicit downcast. So you use self whenever you want to. If you thought about using this in the past, you want to use self instead. It's really more of a convenience than explicitly writing out that static cast syntax, because it's very long and awkward in some cases to write out the full static cast of your concrete class. But the onus is on the developer to actually do this. There isn't really any sort of C++ requirement that you actually have to do this. It may just work it may appear to work just fine, but you may get bad things happening on you. And I'll talk a little bit more about that in a couple of slides, because we have some tooling that helps with some of this. Okay, so how do you actually use extensible classes? Well, the way you simply have to instantiate the concrete class, right? So in that instruction hierarchy, you would instantiate a tr::: instruction to actually create an instruction. You don't ever instantiate any of the extension classes at all. The source file should include the concrete class header file without any sort of project or architecture specializations. So in this particular case, in the code generator, we're just going to be including code generator.hpp. We're not saying, give me the X code generator.hpp. You're trying to let the generalities work as they're supposed to, and let the iPads resolve everything for you. Do not use concrete class header files in other header files. So this statement really kind of goes back to the problems that we were having very early on with this when we were trying to open source this technology, where everything was very connected to each other. So you would have, for example, the code generator class would include the instruction hierarchy, which would include the compilation, which would include register dependencies, and everything would end up being pulled together into one big, large bolus of code. And it was very difficult for the include mechanism that we come up with to actually work, because the ordering was very important and you had to sort of resolve these dependencies. So the general advice here, and strongly recommended, that you don't actually include concrete class header files in other header files. Most of the time you can just get away with using forward declarations. And the other thing is to actually member functions, calling member functions. So if you actually inline code in your header files, and that ends up calling a member function, you're going to have to include a concrete header file somewhere to resolve that. So the general advice is to not call member functions from within any inlined code. So in practice, so this was, I guess, maybe about 6 months old now. So at that time we had about 67 extensible class hierarchies in OMR. This definitely didn't cover all the class hierarchies, but there were a lot of them. If you do decide to make an extensible class hierarchy, that doesn't mean that you can't use virtual functions. There are good uses of virtual, like you can mix the two, static polymorphism and dynamic polymorphism. So for example, we have, I guess that's the next bullet here. If you look at, in some cases, the base, you can provide a sort of a common base class, which is defined by static polymorphism, but then you can create a dynamically polymorphic hierarchy from that. So if you look at the instruction hierarchies themselves, they are actually all dynamic polymorphic hierarchies, but they are built from a base class that has been defined statically. So processor instruction hierarchies and the optimizer itself, it still uses dynamic polymorphism. Okay, so I talked about classes. I just quickly want to show you how we use this kind of same technique to extend other data structures as well, because if you look through the code, you're going to see the use of static tables, you're going to see the use of enumerators, you're going to see unions in some cases as well, and there are ways of actually applying this kind of trick with the IPath to those structures as well. So here's an example of how the opcode, the IL opcodes names are actually defined. So this is actually an enum. And if you look at how it's actually defined, in the TR namespace, that's where the IL opcodes enum lives, but the data part of the IL opcodes is actually just a pound include. And it includes something called IL opcodes enum.hpp. And the way that this works is that given how the IPath is set up, it'll find the most specialized implementation of IL opcodes enums.hpp, which in this case, it's found one in TRJ9. And what you would find in that file is something that looks like this. And what it would do is actually include the J9 specialization of that IL opcode enum. So that would look like this. And the first thing that it does is it reaches back and includes the OMR implementation of it as well. And then that does something like that. And then eventually what ends up getting produced is the composition of all these, which looks like that. So using that same kind of trick of with iPath magic, we can basically compose and extend enums as by project. So it turns out to be a fairly useful way of doing that. And you can do the same kind of trick with static tables as well. Unions are a lot more problematic, and I don't think we actually have a great solution for that. I'll get to that in a sec. But anyways, this is how you put together enums if necessary, and you're going to see this in the code as well. You look into it. So we do have some tooling to make some of this easier. One thing that actually we have is a linter. It actually checks that the extensible classes, provided you've used the OMR extensible attribute, it can check a variety of things to make sure that the classes are put together properly. So for example, it can actually tell you when you're missing this point. If you're using this implicitly and you're missing a self call, it'll actually flag that and it'll fail to build. We do run this kind of a checker on every build in Eclipse OMR. There is a linter job that runs that'll do this over the code, so it'll reject anything that fails like this. There's also tooling to help rewrite classes. So if you came across, and this isn't necessarily as useful as it was in the past, but if you come across a class hierarchy that isn't currently extensible but you'd like it to be, there are some tools available. They're all based on Clang. That's actually what the OMR checker is based on. It's a sort of a Clang tool to actually to help you rewrite the class using the right kinds of rules for extensible classes. So it'll help you insert the self calls whenever an implicit this is found and that sort of thing. Now we use that on this is an example. We use that on the node class when we did that work. So. There's actually a research group at the University of Alberta that's been doing some work on projects like this, and they've actually been helping us to develop some tooling to aid with further ways of validating extensible classes and figuring out when, what parts of the class are extensible. Maybe there are parts of the hierarchy that we have missed extending, like we should have extended, but we didn't, that sort of thing. So they've been very helpful in developing some of this tooling. So maybe someday we can actually start using this in our validation parts of the build to give us more insights. And getting close to the end here, but just some limitations with this. I mean, there's lots of limitations with this. Let me be perfectly honest with it. It's not a perfect solution. But it works fairly well, and like I said, we've taken several iterations at this so far, and this is sort of the best we've come up with so far. So one limitation that you're going to come across is with constructors, and one of the challenges is really with the way that if you have architecture specializations that want to introduce a constructor that has their own sort of special parameters, it's difficult to extend those sorts of things, because if you look at the way that the hierarchy will eventually put itself together, it's going to be sort of woven in between architecture specialization and non-architecture specialization. So there are situations where if you want to actually provide custom parameters to your constructor, it's going to be difficult to do. We've actually prototyped, I don't know if that code ever actually got committed, just an example piece of code of a way of actually putting like a chain of these constructors together that allows you to do architecture specialization. It has to do with by passing up like another class altogether, and that class contains all the different things that you might want to specialize. Maybe have to dust that code off. If anybody's interested in seeing that, I can dust that code off, find it, dust it off, and get it out there. It hasn't really bitten us too much, the fact that you want to provide your own constructor, but it might in the future. We may need to actually have a better solution here. The other thing is, how do you actually go about identifying extension points? So right now, anything in these classes is an extension point, and that could potentially be problematic. So what if we only wanted to, I wanted to provide a class that only has 2 extension points. That's the only thing I wanted the user to be able to specialize. That's not really possible right now. So we need to potentially think of ways of doing that in the future, but not quite sure we have a great answer there yet. If you start using self a lot, you can see it all over the code, and it can make the code look kind of ugly. Like I said, if you look at the node class, you'll see it a lot. It can make the code ugly to look at, and it's probably one of the bigger pain points that people have with this technique. So the other thing is inline function implementation and extension class header files. So it's difficult to provide an inline implementation in some of these class header files for the reasons that I said earlier, in that you actually have to include the concrete class, which starts to pull in a lot more stuff. And you're going to start to get circular dependencies between some of these class hierarchies, and that's not going to, they're not easy to resolve. So we need better solutions to that, and also how do you apply this technique to unions? We started experimenting with it to see if we can come up with some solutions. We didn't get too far with it. Where you're going to see a lot of this is like in the node class. The very base of the node class has got a lot of unions to save space, and it's difficult to tear those apart and make them extensible. So we're still thinking about that, but any ideas are welcome. And then just how things we can do with this going forward. We were thinking about backing off our initial position about so in practice, there's actually not that many functions that actually get extended or specialized in any sort of given class hierarchy. So what we thought about doing was actually using the framework of composing these classes, but the actual extension parts just using virtual functions. And we don't think that you would actually get a lot of performance impact from that, but we wanted to measure that. But the idea here as well is that we get rid of all those self calls, because if they are virtual calls, they would get resolved naturally at compile time or at runtime. So the code would look a lot better. So there are some potential performance issues, but we wanted to measure those. So I think there's actually an issue open for that. I need to dig that out. Add more C++ annotations and extensible classes. Yeah, we could potentially annotate what the extensible parts of the class are. So instead of, for example, using virtual, as the previous bullet said, we could actually annotate them to say this is the extension point. And we can actually provide tooling to help validate that. And now that we are actually much further along than we were like 4 years ago in terms of decoupling a lot of the code, a CRTP solution might actually work a little bit better now than it did back then. So there is the potential of investigating that in the future, but it's not really very high on the priority list right now, just because of the disruption it's going to cause, because it's going to be a fairly big refactoring to do that. But who knows? It might actually work. So, okay, so that's a whirlwind tour of extensible classes. I think that, to be completely honest, I think the way that you can really learn these the best is to actually just spend some time in the code, to look at how some of the classes, like the code generator, like compilation, like register, that kind of thing, are all put together, and just sort of understanding how the connectors work and that sort of thing. So I'm happy to take any questions now. Happy to take any questions in the future as well. If you come across anything you don't are not quite sure about, by all means, speak up. But anyways, I'll stop now and take any questions you have. And if there aren't any, I guess we could adjourn. I think the next call that I'd like to do, we'll start to touch on the meanings, the semantics behind some of the classes in the code generator. So the things that we actually have to start fleshing out. So for example, the machine classes, like the register dependencies, registers, instruction hierarchies, that kind of stuff. Start talking through some of those. Once we have an understanding of that, then others can start building, that you guys can start building out those, the implementation of those, right? Going to the A64 instruction set and start adding, and start creating those. But let's get the semantics down pat first, and then we can go from there. So no questions then?
I'm okay.
Okay. All right. So if there are nothing, I will, I guess we can adjourn right now. And if you have anything in the future, just reach out.
Okay. Thanks a lot, Darryl.
Okay. All right. Thank you.
Thank you.
Bye.
Bye.
Thank you.